Large-scale visual localization asks a simple but fundamental question. Given a query image, where is the camera in a known environment? This problem is essential for augmented reality, autonomous navigation, robotics, and large-scale 3D scene understanding. In this work, we present CoLoR, the devil is in scene coordinate regression for large-scale visual localization. Today, the most accurate localization systems are usually based on feature matching. They build an explicit 3D map, store many visual descriptors, match 2D query features to 3D points, and then solve the camera pose. These methods are accurate, but the memory cost can be very high, especially in large-scale scenes. Scene coordinate regression, or SCR, offers a compact alternative. Instead of storing millions of descriptors, SCR encodes the scene inside a neural network and directly predicts the 3D scene coordinate for each image pixel. However, while SCR works well in small scenes, it still falls behind feature matching in large-scale environments. Why does this happen? We identify two key challenges: sparse co-visibility and local appearance ambiguity. In a small scene, many points are observed from multiple views. This makes it possible to learn geometry through multi-view consistency, but in a large-scale scene, many points are only observed once. We call them single view points. Previous SCR methods still sample these points during training, but reprojection-based supervision cannot effectively train them. At the same time, even multi-view points become less frequently observed, making implicit triangulation weak and unstable. The second challenge is appearance ambiguity. Large environments contain many repeated structures, similar windows, walls, floors, signs, and corridors. Local patches may look almost identical, even though they belong to completely different 3D locations. CoLoR addresses these challenges with a new training framework designed specifically for large-scale SCR. The first idea is simple. Instead of treating all sampled pixels equally, we explicitly partition scene points into multi-view points and single view points. To do this efficiently, we avoid exhaustive pairwise matching. For each image, we only match it with its top co-visible neighbors using a co-visibility graph. This reduces the matching cost from quadratic to linear in the number of images. After filtering incorrect matches with epipolar geometry, we know which pixels have reliable correspondences across multiple views. For these multi-view points, CoLoR applies explicit multi-view reprojection supervision. Rather than supervising each observation independently, all views of the same 3D point jointly constrain one predicted scene coordinate. This creates a much stronger geometric signal because the predicted point must be consistent across multiple camera views. But what about single view points? They cannot be triangulated, so multi-view supervision is not available. A monocular depth model could be used, but monocular depth usually lacks metric scale, which makes it weak for localization. CoLoR solves this with a bootstrapping strategy. After the first training stage, the SCR model can already predict reliable geometry for many multi-view points. We use these predictions to generate a sparse metric depth map. Then we keep only high-confidence pixels with low reprojection error and feed this sparse depth into a depth completion model. The result is a dense pseudo-depth map with metric scale. In the second stage, CoLoR trains on both the multi-view points and selected single view points, using pseudo-depth supervision to extend learning to parts of the scene that previous SCR methods could not effectively supervise. The second component of CoLoR is a more consistent feature representation. Previous large-scale SCR methods usually concatenate two kinds of features: a global retrieval feature at the image level and a local matching descriptor at the pixel level. But these two features are optimized for different objectives. The global feature is trained for retrieval across large areas, while the local descriptor is trained for matching within nearby views. This creates a mismatch. CoLoR reframes both features as retrieval representations at different granularities. The global descriptor performs image-level retrieval, and the local descriptor is retrained for pixel-level retrieval. Using a contrastive learning strategy with a MoCo-style queue, The model learns to pull together descriptors of the same 3D point while pushing apart visually similar patches from different regions. This makes the final feature more discriminative for large-scale localization. We evaluate CoLoR on both outdoor and indoor large-scale benchmarks, Aachen Day-Night and Hyundai Department Store. On Aachen Day-Night, CoLoR achieves highly competitive accuracy with only a 47 megabyte map, significantly smaller than feature-matching base systems. On Hyundai Department Store, the improvement is especially clear. On the 4F test set, CoLoR improves the strict localization accuracy from 60.2% to 80.9% compared with R-score, while keeping the map size at only 50 megabytes. In contrast, feature matching methods require tens or even hundreds of gigabytes of map storage.